Hey everyone, so what is consensus? You've probably heard this word thrown around in crypto and blockchain spaces, but what does it actually mean? Well, let's dive in and figure out how a bunch of computers scattered around the world can agree on anything without a central authority telling them what to do. Alright, so here's the fundamental challenge that keeps computer scientists up at night. In a decentralized network where there is no central authority, no boss, no referee, how do all these independent nodes decide on what's actually true? I mean, think about it. This is a really hard problem, right? You've got all these computers around the world, let's call them nodes. Each one is independent, each one has their own view of what's happening. Notice how each node has this dual layer design that's representing the complexity of this distributed systems. Now, let's say Alice wants to send Bob 10 bucks. All five nodes see this exact same transaction request. In a centralized system like your bank, one computer would just process it and that's it. But here, what if these nodes disagree about whether Alice has the money? What if some nodes are offline? And what if some are malicious and trying to double spend Alice's money? What if network delays mean some nodes get different information at different times? Without a referee, without someone in charge, how do you prevent this chaos? This is the consensus problem in a nutshell, getting independent parties to agree on a single version of truth. Enter consensus mechanisms. These are basically sophisticated rule books that tell distributed networks exactly how to make decisions together. A consensus mechanism is a set of rules that allows distributed nodes to agree on a single version of truth. Think of it as a constitutional framework for a digital democracy. But here's the thing, any good consensus mechanism needs to satisfy three critical properties, and getting all three right is incredibly difficult. First, safety. No conflicting decisions. You can't have Alice's payment both succeed and fail at the same time. The system must be consistent. Everyone agrees on what happened. Second, liveness. Progress is always made. The systems can't get stuck in endless debate or deadlock. Even when things go wrong, the network has to keep processing transactions. And third, fault tolerance. Works with bad nodes. The system must function even when some nodes are offline, broken, compromised, or actively trying to attack the network. This is the really tricky part. Sounds simple, right? Well, this is actually one of the hardest problems in all of computer science. It's called the FLP impossible theorem. You literally cannot have all three properties perfectly in an asynchronous network. Let's start with granddaddy of them all, proof of work. This is what Bitcoin uses, and it's absolutely brilliant in its simplicity. Picture this, you've got four miners. These are specialized computer competing in mathematical race. Each miner is represented by these orange boxes, and they are all racing to solve the same puzzle. The puzzle, find a number that when you combine it with all the transaction data and run it through a hash function, gives you a result starting with multiple zeros. The more zeros required, the harder the puzzle. All four miners start computing like crazy, trying billions of random numbers per second, burning massive amounts of electricity. It's pure computational brute force. There's no shortcut, no clever trick. And boom, miner 2 gets lucky and finds the magic number first. Look at that green highlight. They found a hash starting with 000A5B3. This took real work, real electricity, and real time. They immediately broadcast their solution to the entire network. Every other computer can instantly verify the solution is correct. Verification is fast, but finding the solution, that is what is expensive. The network accepts this block because someone proved they did the computational work. The energy expenditure makes cheating extremely expensive. That's consensus achieved through proof of work. The longest chain with the most accumulated work wins. Now, proof of work burns enormous amounts of energy, so brilliant minds came up with proof of stake. This is what Ethereum switched to in 2022, and it's a completely different approach. Instead of miners burning electricity, you've got validators who put up their own money as collateral. Look at these four validators. They have staked 100, 50, 200, and 75 ETH respectively. This isn't play money, this is the real cryptocurrency they could lose. The algorithm selects a validator to propose the next block, and it's not random, it is weighted by stake size. The more money you put, the higher your chance of being chosen, but also the more you have to lose if you misbehave. Validator 3 gets chosen because they've got the biggest stake with 200 ETH. They have the most skin in the game, so the network trusts them the most. Economics replaces electricity. They propose a new block filled with transactions to the network. All other validators examine this proposal carefully. Other validators attest that the block looks valid. They are essentially voting with their stake. If anyone tried to cheat or propose invalid transactions, they'd lose their stake money through a process called slashing. Consensus achieved with 99.9% less energy than proof of work. But wait, there is more. The crypto world has gotten incredibly creative with consensus mechanisms, each solving different problems. Delegated proof of stake is like representative democracy for blockchains. You've got regular token holders, those green dots, who vote for delegates represented by the purple circles. Instead of everyone participating directly in consensus, you elect representatives who take turn producing blocks. It's faster, more scalable, but potentially less decentralized. Then there's another practical Byzantine fault tolerance. This is that many enterprise blockchains use. Look at this 3 by 3 grid. You've got 9 nodes total with a red one in the center acting as a leader. It's got a sophisticated 3-phase protocol. Pre-prepare, prepare, then commit. Every decision goes through these 3 voting rounds. The amazing thing is, it can tolerate up to 1/3 of nodes being completely Byzantine, meaning malicious, compromised, or behaving arbitrarily. That's incredibly robust, perfect for when you need instant finality and can't wait for multiple confirmations. Okay, so a quick history lesson that'll blow your mind. This whole consensus thing relates to a classic 1982 computer science problem called the Byzantine generals problem. Imagine you've got 5 generals surrounding an enemy city. 4 are honest, shown in blue, but one is a traitor, shown in red. They need to coordinate whether to attack or retreat, but they can only communicate by sending messengers. The honest generals all want to attack and they send attack messages. But the traitor in the middle, he's sending a retreat message to try to sabotage the coordination. Some generals might receive conflicting information. So, how do you coordinate when you can't trust everyone? How do you distinguish between a traitor's lies and a legitimate disagreement? How do you handle messages delays or lost messages? This is exactly the problem blockchain consensus mechanisms solve every single day, but at massive scale with thousands of participants instead of just 5 generals. Every Bitcoin transaction, every Ethereum smart contract, they are all solving Byzantine general's problem in real time. Now, since we're dealing with money and critical data, let's talk about what happens when sophisticated attackers try to break these systems. Spoiler alert, it's really hard. The famous 51% attack is a nuclear option for blockchain attacks. If someone controls more than half the network's computing power or stake, like the split showing 7 malicious nodes versus 6 honest ones, they can potentially double spend coins and rewrite transaction history. But here's the catch. For major networks like Bitcoin, this would cost billions of dollars and would be immediately detected. In proof of stake, there's this theoretical thing called a long range attack. An attacker could use old private keys to create an alternative blockchain history from way back. That's the red chain versus honest green chain. They're essentially trying to rewrite ancient history. Sounds terrifying, but modern proof of stake chains have clever defenses like checkpointing and weak subjectivity that makes this attack impractical. So let's put our main players head to head and see how they stack up. This comparison table tells the whole story. Proof of work has high energy, slow transaction processing, but very high security. It's like the armored tank of consensus mechanism, proven over 15 years and never successfully attacked. Proof of stake, low energy consumption, fast transaction processing, and high security, more like a high performance sports car. Newer but increasingly proven with sophisticated economic incentives. But here's the fundamental reality of distributed systems. It's all about trade-offs. No perfect solution exists. Want maximum security? You might sacrifice speed and energy efficiency. Want blazing fast transactions? You might give up some decentralization. Want energy efficiency? You might introduce new attack vectors. That's why we have this entire ecosystem of different consensus mechanisms, each one optimized for different use case, different priorities, different threat models. Let's talk about a crucial concept that confuses a lot of people: finality. Basically, when can you be 100% absolutely certain that a transaction will never be reversed? Bitcoin uses what's called probabilistic finality. Each additional block makes a transaction exponentially more secure, but you can never reach absolute mathematical certainty. Watch these percentages: 50, 75, 87.5, then 93.75, and so on. 6 confirmation gets you to about 98.44% confidence. Good enough for most purposes, but still technically probabilistic. But systems using Byzantine fault tolerance mechanisms give you absolute finality. Once a transaction moves from pending to final, boom, it's mathematically impossible to reverse. No takebacks, no rollbacks, and no what ifs. It's cryptographically guaranteed to be permanent. Different tools for different jobs. Need maximum certainty for large transactions? Use a system with absolute finality. Don't mind waiting a bit for ultimate security. Bitcoin's probabilistic finality works great. Alright, now enough theory. Where is this stuff actually being used to solve real problems in the real world? Bitcoin, the original gangster, still uses proof of work after 15 years. It's processing millions of dollars in transactions every day, securing a $1 trillion network. Ethereum made a historic switch to proof of stake in 2022. Now it's processing way more transactions while using 99.9% less energy. Smart contracts, DeFi, NFTs, all running on consensus. Voting systems. Imagine elections where every citizen can independently verify their vote was counted correctly, where recounts are instant, where election frauds becomes mathematically impossible. Distributed databases. Major tech companies use consensus algorithms to keep their data synchronized across dozens of servers worldwide. When you use Google or Facebook, you're benefiting from consensus mechanisms. From digital money to democratic process to enterprise data management, consensus mechanisms are quietly powering the transition to a more decentralized, more trustworthy digital world. Let's talk about economics because these systems don't run on hopes and dreams. They run on carefully designed economic incentives. Bitcoin's global mining network burns roughly $40,000 worth of electricity per day. That sounds like a massive waste, but that energy expenditure is precisely what makes the network so secure. It's expensive to attack. Compare that to Ethereum's proof of stake network, which consumes maybe $50 worth of electricity per day for the entire planet. Same security level, virtually no environmental impact. That's proof of stake achieving a 99.9% energy reduction while maintaining security. It's one of the most significant efficiency improvements in the history of computing. But here's the deeper insight about economic security. It's all about making attacks economically irrational. Cost to attack Bitcoin is over $10 billion, and annual security budget is around $1 billion. So, as long as the cost to attack exceeds any possible profit, the system remains secure through pure economics. Attackers aren't just fighting cryptography, they are fighting mathematics, economics, and the collective economic interest of thousands of participants worldwide. So, what's next? The future of consensus is absolutely wild. We're just getting started. We're starting to see hybrid systems that combine the battle tested security of proof of work with the energy efficiency of proof of stake. Imagine getting Bitcoin level security with Ethereum level efficiency. Then there's the quantum computing threat. When quantum computers mature, and they will, they could potentially break the cryptographic foundations of concurrent blockchains. Future consensus mechanisms need quantum resistant cryptography built in from day one. And sharding. This is the running multiple consensus processes in parallel to handle exponentially more transactions. Look at these four different colored shard chains, each processing transactions independently, all coordinated by the beacon chain below. It's like having multiple checkout lanes at the grocery store instead of just one. Multiple parallel chains dramatically increase throughput while maintaining security through sophisticated cross-shard communication protocols. So there you have it. Consensus is fundamentally about achieving agreement without having to trust any central authority. It's about mathematical and economical guarantees instead of institutional trust. Let's recap the key insights. Consensus solves a distributed agreement problem that seemed impossible for decades. We now have multiple mechanisms with different trade offs for different use cases. And most importantly, consensus is literally the foundational technology that makes all blockchain systems possible. From Bitcoin's energy intensive but ultra secure proof of work to Ethereum's efficient proof of stake to the exotic mechanisms we'll see in the future. Consensus is how we are building a more decentralized, more trustworthy digital world. That's Consensus Explained. If this helped clarify one of the most important concepts in computer science and cryptocurrency, subscribe for more deep dives into the technology shaping our future.